Hi, my name is Clay Rao. I'm part of Group 8 in Stats 380, and this is my log for our project. I'm going to start with our organization. I'm part of the Stella Bain Syndicate, which is a decentralized organization that specializes in extra-dimensional risk assessment and containment. We like recruiting individuals with an uncommon resilience and cognitive strain under pressure. I'm one of our 5 crew members, and our planet was overrun by zombies, which now we are also facing the 10 months journey to our destination point alongside the other teams. The overall goal that we have is to make it to our assigned weak spot as quickly as possible and start preparing to destroy it along the way. So me personally, I'm the maintenance guy on our ship. I'm good at math, knowledgeable about mechanics and problem solving. I'm a hard worker. I think I'm strong, and I'm all right getting dirty to fix a problem. So, the first problem that I encountered, which is we have to land in the North Pole. That's our destination. And we're a little bit worried about our ship's batteries because they are lead acid, and lead acid batteries naturally have poor cold temperature performance. So our ship has 8 batteries total. We need at least 4 of them to last in order to get back off of the planet or the North Pole. So I figured out that there's a 10% chance of any of our batteries failing each day we are there. Um, in theory, the weak spot should take around 5 days to destroy, and that being said, each battery has a 10% chance of failing for each of those 5 days. Um, so I did a little math here to figure out our probability of being able to leave. That is the probability that there's still 4 or more batteries working at the end of those 5 days. So if we know each day there's a 10% chance of failure, so the chance that they survive is 90%. 90% for 5 days. The probability of surviving that a battery survives becomes 59.049%. And we have 8 batteries total. So if we use a binomial, n equals 8, p equals the same 59%. That ends up being 72.83% chance of our ship being able to leave, which I personally think is a risk that we should be willing to take. Um, the next problem that I wanted to figure out is if the other teams are not able to break their weak points, what are the chances that we can go to 5 destinations and help them out? So these 5 locations would take approximately 12 million miles traveled, and the ship's engines are designed to last around 5 million miles on average. Luckily, we have 2, and our ship can still fly using just one of them. So, what is the probability of making the 12-mile trip is the answer that I'm trying to solve. This is a continuous gamma problem. So, with lambda being 1 over 5 million, the probability of our engine surviving the 12 million mile trip becomes 0.173% chance. So the chance that both fail minus the chance that the one survives leaves us with about a 17.3% chance that we can make the trip having one engine left. The last thing I wanted to look into is the trip time for each group. So we want to assess whether the team travel times significantly differ from the expected value of 10 months. And so for this, I used a two-tailed test with the null hypothesis being that the mean is equal to 10, no difference, or the alternative hypothesis is mu does not equal 10, so there is a difference. And assuming that we randomly sampled travel time estimates from 12 teams and that we find a standard mean of 9.4 months and a standard deviation of 0.8 months, and we use a t-test with the standard of alpha equals 0.05. Using the t-table, we find that t is equal to negative 2.6. Using degrees of freedom, which is 11. And then using the table, we find t critical is plus or minus 2.2. And this means that we reject the null hypothesis because the standard 2.6 is greater than our critical of 2.2. So most teams' travel time is different than 10 months. That should say different. And this is significant since it could disrupt the coordination of all of our teams and provide confusion for other teams. So this is not good. And so the p-value is another way that we can figure this out. Having a p-value of 0.0252, which is less than alpha of 0.05, which further verifies that the null hypothesis is wrong, there's a significant difference. And the last way that we can figure this out is using our confidence interval. So we found that our 95% confidence interval is the mean plus or minus 0.5086, which gets us 8.89 and 9.91. Since this interval does not include the 10 months, this further supports that the conclusion that the average travel time significantly differs from 10 months. Next problem, we have three different types of engine oil that we can run in our engines. We can choose fully synthetic 5W30, semi-synthetic 5W20, and conventional 5W40. Each oil type will slightly affect the engine's operating temperature, and since this is a ship, operating temperature is pretty critical. So I measured the running engine temperatures at 10 different points throughout the day, running each engine oil type, and I came up with these three tables of data. And I used a little bit of R code to figure out if there is a significant difference between um, either any of these three sets of data. So my null hypothesis, of course, is that there is no difference. Alternative hypothesis, there is a difference between two or more of the groups. And what I found, given this picture here, because of the intervals of 8 to 8.4, these p-values are not within the confidence interval here for any of the three groups. So that means that there's no significant difference between any of the three groups. And the result of this is that I'm free to use whatever oil I deem best for our engines. Um, so this is the code that I used, um, and that is the end of my log for group 8.
Hello. So today we'll be going over my logbook throughout my journey. So we'll start the log on the first day. So for our group, I was the weapons keeper. So my goal was making sure the training times were correct, weapons were properly functioning, so that everyone was staying up to date and able to use the weaponry they needed. So I had originally planned to sharpen the knives once every single day, each everybody's knife, but each time you sharpen the knife, there was a 1 in 1,000 chance of it breaking. So to model the knife's breaking with sharpening, I use the geometric model here to find a better way to sharpen the knives or actually know when to sharpen them. So using this model with a 1 in 1,000 chance of breaking for our 300-day encampment, so 10 months, 30 days a month about, the probability that the blade will break within 300 days was about 26%. And then you can see the results for all of these with the geometric model. So ideally, I wanted to find one where the probability of the blade breaking was under 10%. So one that fit around that was 100 days. So once every 3 days, the blade would be sharpened. After just even the first day after using this geometric model, I knew that I shouldn't sharpen them every single day if I wanted to make sure our knives were staying in good condition. So yeah, I just want to minimize the probability. We only have so many knives here. After that, we wanted to make sure that everyone was getting a certain amount of training time. So usually we wanted everyone to get 1 hour training time, but in, and training times were anywhere from 20 to 120 minutes to use our space for training. This could be blasters or knives or heavy weaponry, and everyone was asked to do so independently. To stay proficient with the weaponry, we wanted to be at 60 minutes or more, but just looking at the way we collected this was the logbooks of just training time. People would write down how long they trained, and then I could use this to see what kind of distributions it was. So for this, it looked to be pretty um, uniform, continuous distribution here for the amount of training time. So I'll look back again at the end of the 5th month, which we'll see in a later log, to see how that shaped out. So also during this time, as a little skill and hobby of mine while working, I started working on a device for the knife sharpening as well. So I knew that once every 3 days was probably going to be our optimal amount of sharpening for the knives to keep them useful, but also to keep them from breaking. So I thought of a machine to further test those knives. So the first part of this, which can be seen here, is using electrical voltage to run through the knife. Because if it run, the easier it runs through, or the more voltage that is kept, the lower the voltage drop, the less impurities that are inside the metal of the blade. So if there were a large voltage drop or a lot of resistance, we know there'd be more impurities or like strain throughout the blade. And then along with that, I could also worked on creating a kind of polymer pillow that the knife could be put into, and then it could be seen how sharp it was. So over these next few months, I worked on that as well, just looking at how sharp the knife is for actual use, but also seeing how many impurities or like strain is inside the metal blade of the knife. So our next main log was at the end of month 3. These blasters here. Over the course of the third month, I tracked our most experienced shooter and our greenest shooter, so the one who had used blaster the least. So over that, I wanted to see how their blaster training time compared to one another using um, a two sample mean test. So originally, I our null hypothesis was that the blaster timing was the same for both of them. Using that, we're able to see that these two actually have different. We're 95% confident that they have different means between the experienced shooter and the new shooter. So we use the z-test and compared the two sample groups, those two groups, and then we got a p-value of approximately 0. So the p is less than 0.05. So we're pretty confident that they do not share the same mean. So the confidence intervals are here. We can see that this one falls between 54.8 and 56.2. This one falls between 42.9 and 46.3. So these don't overlap, so we can confidently reject the hypothesis that the training times for both groups are the same. Also, along with this time, I got done with the polymer pillow for the knife sharpening. Check when the knives actually need sharpening and reduce the time to probably about 50 days out of the 300 starting here. So the 50 days number was about 5% of the knives breaking over that amount of time in the geometric model. So our next log was at the end of month 5. So this was the uniform model that we used to track the training times of everybody. So the uniform model results are mean of 68.43, standard deviation 27.66. So we have a confidence interval here of where the mean actually is, 95% confidence. But then we also had the probability that training time was above 60 minutes, which was um, our time for where training was adequate and would keep you at a maintaining level. So with a uniform model, it's about 60%. And then also with the real log results that we were collecting, we found the group mean was 74 minutes. Standard deviation was 26.9, and then 95% confidence interval is also here. We can see it's just raised up by about 5 on each. And then using that, probably the training time being sufficient was 66%. So these do not overlap and they're not the exact same model, but they are pretty similar and show a pretty uniform distribution across it. I want to get that up to at least 80% of training times or above the 60-minute threshold of training per day. We'll go to the next log, which is at the start of month 8. So this one is just introducing something that I was looking at the time. So each person should be sufficient in all three of their main weapons, which were the knife, the blaster, and the heavy artillery. And this was our three-group ANOVA test and seeing there's any significance there if we need to step up training in a certain portion of our weaponry. So this is at the end of that month. We're going to look at the results of the heavy artillery, blaster, and knife. So once again, the ANOVA test was used, and we talked about the null hypothesis of them being the same. So these are the differences. So blaster B, knife K, heavy artillery H. So these are the difference in confidence intervals. These two intervals do overlap, so we're 95% confidence that the mean of the two, we cannot reject our hypothesis that they are the same. And then also our p-adjusted is 0.85, which is greater than 0.05. So our intervals, we have negative on the lower and then negative also on the upper. So those two means we're 95% confident that they don't overlap. And that shows also in our p-values as they're both less than 0.05. So we can reject that null hypothesis and show that our heavy artillery training time, we're 95% confident that they have not been the same mean or average as the blasters and knives, which we have been training with this entire time. So this will help us in the ninth month in getting us better at heavy artillery since we're going to need to use that. So end of month 10, we've been using our knives by the Celebane Syndicate, which is who we work for, which is our company. But since we've been breaking some, we also found some knives in the wild. These are the knives found in the wild. These were just sketches that I drew out, and we'll bring some back with us. Hopefully they don't break after we've made it through. We can bring them back to the Stellabane Syndicate. We can look into these because the knives found in the wilderness were working pretty well. And you can read more about them inside of here, but they're much better for combat than these knives, which are much more for just surviving in the wilderness.
Hello, this is Antonia, and I'm going to be walking through the data I used to improve our food scavenging strategy here in the Stella Vein. We've been struggling with food shortages because of the unpredictable scavenging tendencies. I wanted to use statistical modeling to get a clear sense of how many trips it would take to find food and how long we should expect between successful finds, and whether one method or tool might give us a better result than the other. First, I used a negative binomial model, and I asked myself, how many trips would it take to get success? To start, I wanted to answer a basic question, what I just asked. How many scavenging trips should we expect to take before we find three successful sources of food? Since we're dealing with repeated independent attempts with a fixed probability of successes per trial, I used the negative binomial distribution. This distribution model This distribution models numbers of trials needed to achieve a certain number of successes. In this case, I assumed the probability of successes on any given trip was about 25%. This is realistic for how dangerous and uncertain the scavenging zones are. Using the formula for the repeated value of the negative binomial distribution, E of x equals r divided by p, where r equals 3 successes and p is the probability of 0.25%, we get E of x equals 12. So on average, it would take us 12 trips to successfully locate three sources of food. That's helpful when deciding how many trips to plan for and how much fuel or energy we'll need to conserve. Next is I use an exponential model to figure out how long it would take between finds. This is essential for rationing planning. So time between random events is modeled well by exponential distribution. I assume that we usually find something about once every 5 hours, which means that the rate parameter lambda equals 1 divided by 5, which is 0.2. Using the cumulative distribution, P of t is greater than t equals e to the power of negative lambda t. We find the probability that we wait 8 or more hours. So if I was trying to see what was the probability of having 8 or more hours without food. So P of t is greater than or equal to 8 equals e to the power of negative 0.16, which is going to be about a 20% chance that we go 8 hours or more without finding anything. It's a big risk, and it tells us that we need contingency rations and perhaps to limit our outings in high-risk windows to avoid long delays without results. Next, I did a two sample z-test to see what group could be better. So I tested group A and group B. Group A hunted alone, and group B hunted, scavenged in a group. Team A gathered an average of 6 food items with a standard deviation of 1.6, and Team B scavenged 5 items with a standard deviation of 1.2. Each had a sample size of 30 scavenging trips. So, after doing the z-test, our p-value was below 0.01, which indicated a statistical significance. The 95% confidence interval for the difference was from between 0.32 to 1.68, meaning the team N reliably performs better. I mean, team B, where they all work together. Practically, this tells us that switching everyone to teams B method would likely improve overall food intake. Now, finally, I wanted to see what hunting tool was best We tested 4 tools: artillery, torch, blaster, and knife. I ran a one-way ANOVA test to see if the average number of food items collected differed significantly between tools. The F statistic was significant, so I followed up with Tukey's honestly significant difference HSD test to pinpoint where the differences were. Artillery came out as the best tool by a clear margin. On average, it outperformed others by 8 to 12 points, with p-values under 0.05 across comparisons. In terms of strategy, that means we should prioritize allocating artillery equipment when planning scavenging teams. So, what do we do with this information? We should plan for around 12 scavenging trips to secure three solid food sources. There's a 1 in 5 chance that we go a full 8 hours without food success, so rations need to reflect that. Scavenging in groups is more effective than scavenging alone, so that should be standardized. And artillery is the best tool for maximizing yield, so we should focus on using that tool when available. This helps optimize effort, reduce risk, and increase food security as we try to survive in this environment. Thank you.
Hi, my name is Kushi, and I'm currently stuck on a ship in an alternate dimension. Let me explain why. My friends and I are on this ship, and basically we're from planet Earth, and the Earth has been taken over by zombies, and not only that, it's been sealed by this light barrier, and the only way that my friends and I can get back to Netflix and chill is if we take our ship and travel over to the weakest point in this light barrier and bomb it. If we bomb it, our planet is ours again, and we can be back home. Again, my name is Kushi Singh, and I am the fuel expert on board this ship, and I need to ensure that we have ample fuel to get to that weakest point in the barrier, and this trip is total going to be about 48 hours. Some of my categorical traits are: I have a background in fuel systems, I'm a huge math nerd, and I love zombies, but from a distance, of course. And some of my quantitative traits are: I'm tall, nearsighted, I have 2 legs, 2 hands, and 11 fingers, because, well, your girl can type. And I also have 2 eyes, because I can clearly see things without assistance. I'll give you some details about our operation. So right now we are on our way to getting to the weakest point in the light barrier, and I need to ensure, like I said earlier, that we have ample fuel to get to that location. So the first problem that we come across is: how are we going to get fuel on this ship? According to my research, we have found there are about 100 fuel ports or spaceports / launch facilities that exist in this dimension. We need to get fuel from about 50 of them, and that will power us up so we can get to that weakest point. Here's the thing though, we don't know whether these spaceports are going to be good for us or not, because the thing is, our tank is not compatible with some of the adapters on these spaceports, and some of these spaceports are also taken over by zombies. So what are the chances that we arrive to a spaceport and it's not taken over by zombies and it's compatible with our fuel system? Well, I ran some numbers on the machine and found that we have about a 90% chance that we'll get lucky. Or not lucky. I guess we'll be able to get our fuel. So we're gonna go ahead and head to these spaceports. Upon reaching the spaceport, so we have been traveling about 16 hours now, and we have ample fuel, but there are 24 hours left on our journey, and I'm just wondering, should we get fuel again? And I ran some numbers again and found that the thing is that on average, the spaceports will provide us enough fuel to travel for 16 hours without refilling, and there are 24 hours left on this journey. So I ran some numbers and found, what are the chances that we run out of fuel before this journey ends? Should we go back and get more fuel? And after running the numbers, I found that there's a 77% chance that we will need to go get fuel again. Thus, we went ahead and got fuel. Upon reaching the spaceport, I'm a little bit confused because I've heard about 2 types of fuels, fuel A and fuel B. The thing is, the talk of the town, or the alternate dimension, I guess, is that A and B are both really good fuel sources. But I hypothesize that there is no difference between them. I mean, this is all just subject to opinion. How do we know one is better than the other? So I don't think so. I don't think A and B are different. And so I collected some data on the mileage that both fuel A and fuel B provide and ran it into my machine. And I actually found that we can reject my hypothesis. There is a significant difference between fuel A and fuel B. That's what the numbers say. And now I need to know by how much. What is their difference? So now we go ahead, we land on the spaceport. And we know there's a difference between A and B, but we don't know how much. But now there's another problem on our hands. There's another fuel type. And there's mixtures. There's actually 3 types of mixtures of fuel types. So no one is purely better than the other yet, so I say. So the thing is, there are about 3 mixtures of fuel, and I gather that same data. How much mileage does each mixture provide us? And I find that since A and B are a part of the mixtures, of 2 of them, and another one is mixture C. And the thing is, A and B are statistically different than one another, but we don't know by how much. And so I run the ANOVA test and find that, well, there is strong evidence that there is a difference among these 3 mixtures still, which is good, but I need to know by how much. So to know that, I perform one of the pairwise tests. And in this, we're going to determine by how much do these mixtures differ from each other. And turns out that mixture B performs better than A, and mixture A performs better than C. So it turns out that fuel mixture B is the best. It will provide us the best mileage, and it will get us to that weakest point in the barrier. Now, just to map how I get to every single launch facility, every single spaceport, now that I know when I need to fill up fuel, I also know what kind of fuel I need to fill up. But in order to find my way to the nearest spaceport, just to make sure that we're being really efficient with our fuel usage, I'm going to implement Dijkstra's algorithm. This algorithm will give me the shortest path between all the spaceports in this alternate dimension. So I'll be able to get to the closest one, wasting the least amount of fuel possible, just because saving on fuel is always a good idea. And this way, our ship has ample fuel and will get us to the weakest point in the barrier. Now we're going to pass it on to my friends.
Hello, my name is Amelia. I am the safety officer on our team, and I'm making this video to record the statistical observations I made during our 10-month mission. So the first problem I had was that I wanted to find the number of attacks a walker zombie makes until their first successful hit. So this was going to follow a geometric distribution, and I started by looking at hundreds of walker zombie attacks in our footage, and I found their accuracy to be about 30% every hit. So this followed a PMF distribution, and I used this distribution to find the probability that it takes 2 attacks to be hit, and I found that that was equal to 0.21 when I plugged in those 2 attacks and the 30% accuracy. And with that 0.21 result, that means there is a 21% chance that one of us will take the first hit on the second attack from a walker zombie. Next, I decided to create another problem to see how long I have to wait between encounters with walker zombies. I used an exponential distribution to model this, and I found that the zombies were typically at a rate of 10 zombies per hour while we're outside, and I wanted to see the probability of an encounter within the next 6 minutes. So I used a CDF, and I got a result of 0.63212, meaning there's a 63.21% chance that my crew member or I will encounter a walker in 6 minutes while outside. I wanted to see if there was a significant difference between Clay's speed at killing walker zombies versus my speed at killing walker zombies. So I looked at our body cam footage and recorded the times, and I did a 2-sample mean comparison following a normal distribution. So my null hypothesis was that our true average time to kill a walker zombie was equal. And then after plugging that in to my system, I found that the value was approximately 0, and with an alpha significance level set to 0.05, that means that there is statistically significant evidence to conclude that there is a difference in the true average time to neutralize a walker zombie between Clay and I. My mean was found to be 3.833 seconds, and Clay's mean was found to be 5.27 seconds. So there's a statistical difference between those two means, and this indicated to me that Clay needed some kind of work to get his speed up. I also found a 95% confidence interval for the difference in means to range from 1.188 to 1.687. This means that the simulation is 95% confident that the true difference in average neutralization time between Clay and me is between 1.88 seconds and 1.687 seconds. Since the interval is positive, this indicates that I am 95% confident my time is greater than Clay's time, or less than Clay's time. The hypothesized difference 0 is not contained in this interval, so this aligns with the decision to reject the null. I also got results for individual confidence intervals, and these results included that I am 95% confident that the true average time to neutralize a walker zombie as Clay is between 5.115 and 5.426 seconds. And for me, I am 95% sure that it is between 3.638 and 4.028 seconds. Next, I did another statistical analysis, and I wanted to see if there was a difference between types of berserker zombies that I've seen. There were 3 different types of berserker zombies that I've seen, including explosive, normal, and then also armored. So my null hypothesis was that each of them would deal the same amount of damage. The true average damage between the 3 potential types of berserker zombies is equal. And I decided to make a comparison using a 3-sample mean comparison following a normal distribution. After inputting that into my system, I found the F statistic to be 8.812. The F statistic is a ratio of the variance between groups to the variance within groups. And then I also found a p-value of 0.00113, which represents the probability of observing an F statistic this large or larger if the null hypothesis is true. And with an alpha level set to 0.05, which is greater than our p-value, I can reject the null hypothesis. So based on my sample data and the system results, the ANOVA results, there is statistically significant evidence to conclude that there is a difference in the average damage dealt per hit among the explosive berserker, armored berserker, and normal berserker variants. At least one group mean is different. Since the F test was significant, a pairwise comparison was used to determine which specific groups differ from each other. And I used an alpha set to 0.05 for this. So when comparing armored versus explosive, on average the armored dealt 0.507 more damage than the explosive, and the 95% confidence interval ranged from negative 0.076 to 1.090, and the adjusted p-value was 0.097, which is greater than the alpha. So there is no statistically significant difference in the average damage between armored and explosive berserkers. For the normal versus explosive berserker zombies, the normal berserker dealt 0.480 less damage than the explosive on average, and the 95% confidence interval is negative 1.063 to 0.103, and the adjusted p-value is 0.122. Since 0.122 is greater than 0.05, again, there is no significant difference in average damage between the normal berserker and the explosive berserker. And then finally, comparing the normal versus armored, the normal berserker dealt an average of 0.987 less damage than the armored berserker, and the 95% confidence interval was negative 1.570 to negative 0.404, and the adjusted p-value was 0.000743, which is much lower than 0.5, meaning that there was a statistically significant difference in the average damage between the normal and armored berserker. The armored berserker deals significantly more damage on average than the normal berserker. The confidence interval also did not include 0, and since both bounds were negative, this also indicates indicates not rejecting the null. I used the pairwise test because the ANOVA test does not show the specific differences between groups. And then finally, one more statistical observation. We were in a new region, and I had rates of zombies per hour that we were observing, but that number changed once we changed location. So I wanted to see if this seemed to change once we moved locations, and I wanted to see if this was a statistically relevant observation. So in other regions, the walker zombies were observed about 83% of the time, and the berserkers were observed about 17% of the time. But in this new region, I had recorded 103 walkers and 39 berserkers, which is slightly different than expected. So my null hypothesis was that there is no significant difference between the true average encounters with berserkers and walkers in this region, meaning that it was not statistically significant that there was a difference. So after putting my values into a system, I found that the chi-squared chi-squared test statistic was 11.829, and the p-value was 0.00058. And using the standard alpha level of 0.05, I can reject the null. And this means that there is statistically significant evidence to conclude that the observed frequencies of walker and berserker zombie encounters in the new region differ from the previous areas. So that means fewer walkers were seen than expected at a proportion of 72.5%, and more berserkers were seen at a rate of 27.5%. And yeah, that was all of my statistical observations. And I'd also like to share that I made a physical documentation of the zombies, just in case. This is it. Okay, and then I also designed the Zula hoop, which is a hula hoop attachment, which is designed to protect against walker attacks since they're kind of dumb. So this protects against walker attacks by attaching to your body. Thank you.